Thanks everyone for coming. Yeah, so I'm going to speak about this project that we've been running since about March or April of last year, so 2022. We've had a working group comprising OpenFF, OpenFE, and folks from the Cadera lab. It's been working on this practically every week for the last year. So the fruit of that labor is Alchemiscale. So this is an open source, high throughput alchemical free energy execution system for use with HPC, cloud, bare metal, and folding impulse. Oh, and I should introduce myself. I'm David Dotson. I'm an independent consultant. I work with OMSF and the Cadera lab. So this has been one of those major efforts for the last year. I don't know if this is working. Oh, there it is. Thank you. So this project was born out of a shared need by several stakeholders. So ASAP Discovery, of which the Cadera lab is a part, needed to advance the COVID moonshot infrastructure into the ASAP Discovery infrastructure. So ASAP Discovery is this open science drug discovery platform, in particular for pandemic potential virus targets. Basically, the current infrastructure that was built from the COVID moonshot just wouldn't scale to the speed of iteration that ASAP Discovery was going to need. Open force field, we heard Lily allude to this earlier, that a benchmarking apparatus for protein ligand free energy calculations, both OpenMM and GROMACS was desirable, basically decreasing the cycle time of iteration from a new idea for a force field to testing it to new force field. So being able to rapidly test new ideas and then rapidly benchmark advancements. And then open free energy would have liked to have a platform for assessing and evolving implementations of binding free energy methods, different atom mapping approaches, different execution strategies, basically everything within their remit. A system like this would be of huge gain. And I just wanted to give the context of where Alchemiscale sits. So the OpenFE ecosystem, as Richard pointed out, it gives a lot of workflow flexibility to users. So in broad strokes, what we're trying to do at all times, we're doing free energy calculations is, we're defining the sets of systems that we're interested in getting free energy differences between. So we're doing drug discovery. We're trying lots of different ligands for a given protein target. We're building these alchemical networks. So we're defining our networks. Then we're executing those networks. We might be using a commercial solution for that. We might be using something that we built internally, something that maybe a bunch of scripts that we threw together and we've been using for years. That could be our execution engine. And then we also have tools for analysis, taking what comes out of execution, what comes out of the expensive part, in order to then iterate on this process, do the whole thing again and again. So reducing that cycle time is a key component of what we're trying to do here. And the tooling that OpenFE draws from. So OpenFE is intended to be kind of a top-level package for users, but it draws from these other packages listed here, like Goofy and LowMap Cartograph. These sit at the defining stage, how we define the work we want to do. As far as execution engines go, OpenFE does expose some ability to execute. I'll be talking about Alchemiscale here that sits in the execute column. And then for analysis, we have lots of other tools and perhaps many other I'm not mentioning here, but these are the ones that are used within OpenFE at the moment. So you might ask, why would we need different things in this execute column? Well, honestly, different tools are more or less appropriate depending on what kind of infrastructure you have access to, what your constraints are within your organization. Basically, there's not a one-size-fits-all solution for execution, typically. And we'll be talking about Alchemiscale here. So what is Alchemiscale? Well, it was in the title, but the longer definition is it's a service-oriented execution system for alchemical networks. So these are alchemical networks as defined by Goofy, suitable for utilizing multiple compute resources. So HPC clusters, individual hosts, pulling at home work servers is something we're anticipating to do as well, to support large campaigns that require high throughput. So if you just want to run a few edges, Alchemiscale is probably not your tool of choice. If you want to run thousands of edges and many networks, perhaps across multiple teams in your organization, then Alchemiscale is appropriate. And you can use all of these resources or different variations of these resources at once with a single instance. We'll see how that works in a second. So like I said, it uses the same core data model as all the OpenFE tools using the Goofy. It's deployable, at least a single server deployment is deployable in a few steps with Docker Compose on AWS. Architecturally, it uses a Neo4j graph database that serves as the central state store. And this uses AWS, and it also uses AWS3 for the object store to hold on to result artifacts, basically the fat stuff that comes back from calculations. User access is provided via an icon client. So this is an HTTP client. It talks to API services that broker interactions between or with the state and the object stores. So it's a standard kind of web services architecture. The compute services that actually do that perform these alchemical protocols or the Goofy model, these can be deployed on resources elsewhere, like set of HPC clusters and hosts, and they will draw tasks from the API services, execute them, and then push the results back. And we're now in production. We've been using this system now for several weeks. The first deployment of Alchemiscale is now in place. It's actually a shared deployment by OpenFE, OpenSF, ASAP, Discovery, and actually Datryllic by extension. And so this is delivering results for us. Irfan Alave, just wanted to highlight you, went ahead and ran a combined benchmark of OpenSF 2.1 against 2.0 for TIC2, MCL1, thrombin, PIF2A, and P38. And just as a scientific side, because OpenSF 2.1 was just a valence refit, we weren't expecting this to really change what we get for free energy calculations against 2.0. So what we expected to see was basically the same results against both force fields. We've largely seen that here. If we saw something different, we'd be concerned. We do have some outliers that we're now looking into, but that speaks to the power of this approach, is that Irfan was very easily able to just declare what he wanted to run, submit it to the instance, and pull results back down, and then iterate. So I'll talk a bit about how it actually works. We already talked about some of the components, but now there's a bit of a diagram. So this is your user workstation. This would be you, the user. You can define alchemical networks. Here's the client. So as I said, users interact with an Alchemiscale deployment via the client. And you can define an alchemical network using OpenFE or its underlying, it's a Goofy data model that's underlying that. That whole network that you define can be submitted to through the clients, and that network is then represented in the state store. So it's fully represented in Neo4j in the graph database. Users, you as a user can then create an action tasks for the transformations in the network. So you can choose, maybe you want to run a few networks to begin with, or a few transformations to begin with. Maybe you want to run them all. You can kind of do whatever you want to do. And these are then picked up via a weighted random selection by compute services that are running on remote resources. So if you have access again to HPC clusters, maybe multiple, maybe a Kubernetes cluster, any container orchestrator that's running these, basically whatever your resources are, you can hook them up to your Alchemiscale instance and they will serve as workers. When these compute services push results, or when they finish, they push the results back to the object store. So again, the fat stuff lives in an object store. In this case, it's 3, and it has references. Each one has a reference in the state store. But as a user, you're living up in this land. Basically, all you had to do was push things, define your network, action tasks, and then pull your results as they become available. So all of that machinery down here is largely abstracted from. Oh, sorry. So that's the basic workflow, but I wanted to point out a few things that Alchemiscale allows or really enables programmatic and iterative evaluation of alchemical networks. So let's say you define an initial network. So this is something you'd like to calculate. You start with something small and you submit it, you action tasks, you get results back. you decide you want to expand it. You can go ahead and do that. And if you, let's say this network shares a lot of chemical systems, these red dots and connections with the previous one, this network takes advantage of the existing results in the database. It doesn't have to start from zero. It literally is just a delta on the existing network. And you can go further. Let's say you decided later you actually just want to trim your network, so you remove some nodes and transformations you calculated previously. They're still in the database, but you're just submitting a network that is a trimmed and expanded version of a previous one. Again, it will share results for transformations that are in common. So this capability of being able to take advantage of existing results for transformations that are already present really does enable rapid iteration and an efficient compute use. You don't have to start from zero every time. You can do smaller deltas and iterate, or very large deltas. And Alchemiscale enables, it really is a multi-org, multi-user system. So there's authentication built in. This is intended to be exposed to the internet. It is a web service. And so let's say you have two networks you submitted. Alchemiscale has this concept of scope, and it serves two distinct purposes. I'm going to illustrate here. Let's say we submitted these networks to this scope. It's the organization OpenFE, it's the campaign benchmark, and it's the project OpenFF 2.0. These networks, because they share, certain chemical systems and certain transformations, they're going to be able to take advantage of the same sets of results. In the database, they're represented as the same objects because they sit in the same scope. By contrast, so you have shared transformation results here. By contrast, this network, which does have elements in common with these over here, it sits within a different scope. Let's say it was submitted by someone who works for ASAP Discovery. It lives in the ASAP org in this campaign, in this project. This will have its own distinct transformations despite them being identical to something that exists in the database. So there's a domain boundary. This is how we partition data and users in Alchemiscale. So the implications of this is that users with this access to the same scopes can directly collaborate in those scopes. And users that have access to disjoint sets of scopes can't see or interfere with each other's work. So it really does allow you to work together if you'd like. So you can see the same things, work on the same pieces. But if you need to silo work, let's say you're a discovery company and you need to partition or put firewalls between certain teams, you don't necessarily need a different Alchemiscale instance for each one. You could use the same one, you just have to set different scope accesses. So as an example, if I'm Irfan over there, he has access to the OpenFE ** scope, so he can hit anything within OpenFE, create whatever he wants in that, as long as it matches his pattern. And then let's say we also have Mike Henry, who's not here, and Yenka, who's somewhere around here. They have access, Mike Henry has access to these two here, and Yenka has access to just the ASAP scope. Yenka and Mike can collaborate over here. Mike and Irfan can collaborate over here. But Irfan can't even see the ASAP stuff, and Yenka can't even see the OpenFE stuff. And so the same system supports both sets of users, both organizations even. But importantly, Mike, who has access to both these scopes, can see both. So it still allows you to very flexibly, if you've got some people who are shared across organizations, they're able to see what they get access to what they need. So release 0.1.2 is now available. Alchemiscale is a fully open source project. It's openly developed on GitHub. You can find it here. The version 01X series, this is the MVP version of Alchemiscale. There are rough edges, there are performance bottlenecks. You could consider this an unoptimized version, right? We're aiming for feature completeness, at least for the initial MVP, but not necessarily high performance. And it does have insufficient documentation. But it said 0.1.2 is the current patch release. So check that out if you're interested. The upcoming 0.1.3 release is another patch release. This will focus on some initial bugs, some bug fixes, some critical features and performance improvements. So our initial users of this deployment spotted lots of things that they would like changed. We're trying to rapidly respond to that, get some fixes out in a new release, deploy, and then they can take advantage of it. Just want to say where we're going. We're coordinating effort for critical requirements and all the projects that Alchemiscale either uses or touches or impacts via that working group. We meet every week. We operate in 2-week sprints through some donated effort from the stakeholders involved. This whole system would not have been possible without that working group. So it's been a pleasure, and I should say, like, absolutely critical to the process. And we're continuing to go to this day. And the upcoming major releases will focus on, in particular, 02 will focus on docs and initial user feedback, so filling in our documentation gap once we have some real users. And then 03 beyond that will focus on new features, new optimizations, and then some targeted refactors, things that we'll take some learnings and then pull the guts out of it, put it back together in different ways. I should say the folding at home compute service that will allow us to take advantage of exascale compute for the ASAP and OMSF Alchemiscale deployment. We'll be working on that over the coming months. This will really enable us to take advantage of a massive amount of compute. I should say that at the height of COVID, the folding at home network comprised about 1.5 exaflops. It was bigger than the top 10 supercomputers combined. And John has a great figure of it would have been, I think, $6.8 billion per year of AWS compute with how big of a cluster that is. So if yeah, being able to have access to that amount of potential compute will really accelerate OMSF's efforts and ASAP Discovery's open science, open pro discovery efforts. So I do want to give credit. Alchemiscale was drawing from a long line of prior art. We are standing on the shoulders of giants. We get a lot of architectural inspiration from DAS, Fireworks, QC Fractal, and SpokeFit. We also got a lot of stated desires up front from stakeholders and potential users via the user stories they provided. If you're interested in this system and you've got a problem you'd like it to be able to solve, feel free to make a user story on the issue tracker. I see all of these, I tag them. We can try to see if Alchemiscale is a good fit for that problem. And if it isn't, we want to know about it. And to reiterate, a single deployed Alchemiscale instance is now enabling continuous benchmarking of force fields, synthesis prioritization for ASAP discovery campaigns, and it's a feedback loop for method development. And presumably it can enable quite a bit more that we haven't even thought of yet. And I wanted to put this out there. If you're interested in deploying and using Alchemiscale, it's fully open source. We do welcome feedback on how easy it is to deploy and how easy it is to use. If you want direct help with deployment and use, or if you'd like to evaluate it for suitability in your own environment, let's chat. I'm here all meeting. We can discuss that. And we do want Alchemiscale to be a sustainable project. We don't want it to be some one-off thing that improves rapidly over time. And we do believe that its adoption can help drive, it can help drive and sustain the OMSF ecosystem well into the future. And in order to realize that future, early adopters are critical. So we welcome those who are interested. Builds on a lot of work. These are the folks that have been involved in the working group over the last year. If I've missed you, I'm so sorry. Didn't intend it. Of course, there are many that done a lot of work that this is building on top of, getting to stand on the shoulders of giants. So grateful for this community, the free energy workshop community that we just attended last few days. All of this is built upon it. So questions?
Up in front, and then Julian. It's not a question, but very common. I just want to say that I think this work is absolutely fantastic. What you're doing is a very unglamorous piece of work, productionizing and industrializing the infrastructure for these types of calculations. And this has the potential to bring lots of benefits to a much wider group of users far into the future. So I'm very pleased. Julian, With the encryption beyond the recovery of scope, beyond that, is it something that you consider?
So are you talking, I do have my, are you talking about encryption at rest, encryption in transit?
All aspects.
Sure. So we do, I mean, all, yeah, sorry. So Julian asked about encryption, so we talked about separation of data, like can different users see each other's data via scopes, but is the data encrypted at rest? Is it encrypted in transit? So communication between, say, the client and the API services is encrypted via HTTPS, so via TLS. So that's in transit. We don't encrypt anything at rest. So anything that's landed on the object store is not currently encrypted. We could add that. It just means there's keys on the API services, and that could be done if that's of interest. Is that something that you would find is critical? Yeah, I think that would be fairly easy to add if encryption at rest is desired. Now, encryption in the database itself in Neo4j can be done, but it kind of starts to make it harder to use. It makes the database model more difficult, but some things could be.
I think it's a permission. Just permission so that people don't see the.
Yeah, we currently do approach the permissions problem via the scopes mechanism. So, and it's the API services that enforce it. So even if a user hacks their client, it doesn't change anything.
So can you actually deploy and extend AWS at this point?
Yes, we have a running instance. Oh, sorry. The question was, have we actually deployed an Alchemiscale instance? Yes, we have a running instance. It's been running for several weeks now. And it's in service to OpenFF, OpenFE, ASAP Discovery. It delivered the results that I displayed early on. Yep.
What does it cost to run free energy on Amazon in terms of dollars?
So the question was, what does it cost to run a free energy campaign on AWS in terms of dollars? So we're not actually, with this instance, we're not running any of the GPU calculations on AWS. Our server, so our Alchemiscale server instance, if I can go back to the architecture, basically everything that was in the green box, pushing the button and nothing's happening. Anyway, the Alchemiscale server is running on AWS and we use S3, but all of the compute services are running currently on Lilac, which is an HPC cluster, or Pacific Research Platform, which is a Kubernetes cluster. So we're currently load balancing across two very different cluster architectures to deliver free energy calculations for that deployed instance. Does that answer your question? Okay.